Okay, good morning, everyone. Welcome back to the Cryosphere Pavilion. We'll be having another one of our early career scientist talks, and I'm very pleased to invite Christina Draeger, a PhD candidate at the University of British Columbia, to come and give her talk. Good, thank you.
Yeah, thanks a lot, Emma, for the introduction, and thanks for listening to my talk. Yeah, I'm a geophysicist at the University of British Columbia in Vancouver, in Canada. I'm just about to finish my PhD, and I'm happy that I can tell you today about community impacts of glacier changes. So we all do know that mountain glaciers are contributing significantly to sea level rise. But today I would like to invite you on a journey with me to Canada and explore actually which dramatic changes glacier melt has for local communities. And how glacier melt actually affects the million of people that are living further downstream. And I would like to start by sharing a story about my fieldwork on Cascavouche Glacier. So Cascavouche Glacier is one of the largest glaciers in Canada. It is more than 60 kilometers long, and it is right at the border to Alaska. And like most glaciers worldwide, the Cascavouche Glacier is also retreating rapidly. So here you can see a photo from 1900 on top, and on the bottom you can see a photo of 2012, and you can see that the terminus, so the lower parts of this glacier, have completely melted away. And I've spent many weeks on Cascavouche Glacier over the last few summers, and together with my colleagues, I set up automatic weather stations to measure the physical processes that do take place on the glacier, such that we can understand better what are the processes that actually make our glaciers melt so rapidly. And so, for example, what we measured was temperature and wind speed at different elevations above the glacier surface. We measured also turbulent fluxes, so sensible and latent heat fluxes, and precipitation and humidity. And so these measurements, they will help us to see which physical processes contribute to melting, but they will also help us to see actually how well the input data that we are currently using from global climate models is actually representing those local fluxes at the surface of the glaciers. And one of the reasons why Cascavouche Glacier is actually so important is because there has been actually a drastic event happening there just a few years ago, which is called river piracy. And this was so first of all, I will tell you what happened there. And so basically, before 2016, the meltwater of Cascavouche Glacier was flowing northwards, and it was flowing through Kluane Lake and then towards the Bering Sea. So Kluane Lake is one of the largest lakes in the Yukon Territory in the north of Canada. But with the Cascavouche Glacier retreating, what happened is that now the meltwater from Cascavouche Glacier has completely changed its direction and is flowing first eastwards and then southwards right into the Pacific Ocean. So I can show you those satellite images again. So if you focus here at the blue parts of the photos, you can see the Cascavouche meltwater going to the Slim River. And now it completely changes direction into the Cascavouche River and then right into the Pacific Ocean. So this shift caused Kluane Lake water levels to drop by several meters. So here in this photo, you can see the drained lake levels. And this lake has been a really important lake for First Nation communities around there, but also for other local communities that heavily rely on the freshwater supply from this lake, but also as a mean for winter transportation and for fisheries, and it's also actually a very important ground for salmon spawning. And this lake is also really important for fresh water supply for all the communities further downstream. So it doesn't have implications only for the local communities, but for lots of people around this lake. So this lake is no longer what it was. And also actually here in Azerbaijan, we can see that glaciers are retreating drastically. And over the past 7 years, the area covered by glacier has shrunk by an average of 18%. And last August alone, mountain lakes saw a 4% decrease in area. And overall, in recent years, the water resources here in Azerbaijan have decreased by 20%. So today what I would like to do is I would like to share how physics-based glacier models can help us understand better how glacier changes affect local communities. And I would like to also give you two examples as glaciers of contributors to hydroelectric power supply and to freshwater resources. However, before we start, I would actually like to introduce you to all the processes that happen on a glacier, introduce you to explain to you how a glacier actually works. So in the winter, the glacier gains mass through accumulation of snow. And in the summer, we lose mass through melting or ablation. And there are lots of processes that contribute to the melting, such as the long-wave radiation, the short-wave radiation, the sensible and latent heat fluxes, so the turbulent heat fluxes, temperature, rain, and all of these processes contribute to melting, besides of temperature. And together, the accumulation and the ablation, we get the glacier mass balance. And there's more accumulations or mass gain in the higher parts of the glacier, and there's more ablations or glacier melt in lower parts of the glacier, which is mainly due to the fact that in higher elevations, the temperatures are colder. And this imbalance in mass is offset by the glacier flow, which is a flow through gravity. And currently, what current models are mostly doing is they model the melt, so how much melts the ablation of the glacier, through temperature alone. So this is what usually happens at regional and empirical models. The advantage of that is that these models are very easy to set up, and they require only temperature and precipitation as input data. And then the other set of models are physics-based models or surface energy balance models that try to replicate all the surface processes that happens on a glacier. But the disadvantage of that is, of course, that we have a lot of data that is required to get into these models, and they're much more complex to set up. However, with usual empirical models, the problem is that we need to calibrate a specific melt factor, which is usually glacier specific, and it doesn't transform well in space and time. And so this is what we try to eliminate with physics-based models that are way less dependent on a calibration, and thus also way less uncertain. For all the glaciers worldwide, we do not have any measurements. We do have more than 200,000 glaciers worldwide, but far less than 1% of all glaciers does have any measurements for calibration. And so to model how the glaciers are changing in a warming climate, I use a glacier evolution model. So I use input from global climate models, from weather stations and satellite data, and combined with climate models. And I feed this data into a model for accumulation, into a model for melt, and then I do have a model for the ice dynamics, so how much ice and snow are accumulated at each elevation of the glacier, and this is giving us the glacier mass balance. And one of the key improvements in my model that I developed is the representation of the surface reflectance, or also called albedo. So surface reflectance is really important, especially for mid-latitude glacier, because there it is by far, so the short-wave radiation is by far the most important factor for glacier melt. And the surface reflectance is basically determining how much of the energy is stored on the glacier and how much is reflected back into space. So the darker the surface, the more energy stays on the glacier and contributes to melting. And the lighter the surface, the more energy is reflected back to space. So here you can see photos from my fieldwork on Cascavouche Glacier, the same spot at different times. The one where you can see just bare ice. The bare ice is quite dark there because we do have lots of cryoconite there, which is like some sort of organic and mineral matter. On the right, you can see the same spot after it has snowed there. So a kind of a drastic difference in the whiteness. So with all of that model setup, I can measure, or I can calculate how much the glaciers in Western Canada have thinned over the last 40 years. So here I show you my study region. Those are around 20,000 glaciers that I've divided into 10 different subregions. And then I'm showing here the thinning from 1980 to 2022. And what you can see is all the glaciers have been shrinking, but there are large differences between the regions. So most of the glaciers have been thinning by around 15 meters, but then there are also some glaciers that have actually been thinning by more than 100 meters over the last 40 years. And some glaciers have completely disappeared in this time frame. And so we've always known that rising temperatures cause glaciers to melt faster, but there are also other factors that actually play a really important role for glacier melt. And this is one of the really important advantages of physics-based models, that we model all of these processes such that we can actually attribute which factors play a role in, or play which role in glacier melt, or play a larger role in glacier melt. So what we found is, especially the decreasing surface reflectance, so the decreasing albedo, has played a significant role in recent years for glacier melt. We also see an increase in long-range radiation, mostly due to an increase in cloud cover that has contributed, next to the increasing temperature, to glacier melt. And so with all of that, I would like to move forward to my examples. So how we can use these physics-based models actually to simulate local glacier melt for communities that live around the glaciers. And the first example that I would like to give you is the Christina First Nation. That is a First Nation community living in the Rocky Mountains, surrounded by mountains. And this First Nation community has been part of a $16.5 million governmental grant for renewable energy for remote communities program. And the goal of this program was to move away from polluting diesel generators for power to clean, reliable, and affordable hydroelectricity, as was stated by the government. So this is a really important project for this community. The problem is just that most of their stream flow, and that's it's important for the hydroelectricity, right, is coming from glacier melt, and glaciers around this community have been decreasing rapidly. So here I modeled the glaciers around this community first with an empirical model and then with a physics-based model. So you can see the physics-based model in dark red and the empirical model in orange. And you can see actually that there is quite a big difference between the physics-based results and the empirical results. For the empirical result, so I did use an empirical model for the surface albedo, which is the most important melt factor here in this case. So what it tells us is actually that traditional empirical models might even underestimate the melt. And this is because here, especially these glaciers around this community, they do not have any observations in the World Glacier Monitoring Service. So we do not have any local observations to constrain our models with. So my message is basically that those physics-based models, they might actually give more autonomy to these communities to model glacier changes with hopefully more accuracy than traditionally used empirical models. So the reason why actually these empirical models performed, or one of the reasons why these empirical models perform not as well is here because they are kind of right for the wrong reasons. So I'm showing in dark red again my physics-based model and in orange my empirical model. And usually what we see is further down the glacier, so in lower elevations, we have lower albedo, so lower surface reflectance, and in higher elevations of the glacier, we have more snow cover, so higher brightness and whiteness of the surface and higher albedo. And the empirical model is just a straight line profile, so it cannot replicate any of the physical processes happening on the glacier. What we saw as well when we did the same experiments with this empirical model for the whole region is that we did not see any decline in albedo over the whole 40 years. That means actually that if models are calibrated, for example, if this kind of empirical model is used for glacier melt projections, they might underestimate glacier melt in coming years because they cannot cannot replicate basically what climate change is doing to different input variables. And the second example I would like to give you is about the Pacific Northwest heat wave in 2021. So glaciers aren't just important for hydroelectricity, they're also essential for our drinking water supply. And well, most of you probably associate this heat wave with wildfires or drastic impacts for human health. So in this heat wave, we had temperatures reached in Canada of more than 50 degrees Celsius. This was really a record in Canada. And it was the first time that these temperatures were actually reached above 45 degrees north latitude. And so this led to 1,400 deaths that could be directly attributed to this heat wave, and also to a loss of billions of sea creatures. But yeah, what is less known is actually the effect of this heat wave on glaciers and on drinking water supply. So what I'm showing you here is a graph of the stream flow response of a non-glaciated basin. That means a basin that is not relying on glacier melt for their stream flow. And in blue, you can see the 40-year average of stream flow, including the uncertainties in shades. And in red, you can see the timing of the heat wave. And in black, I'm showing the stream flow of the year 2021 of the heat wave. So what you can see that during the heat wave, there's a strong response in stream flow, which led to extreme flooding in that area. And after the heat wave, we had extremely low flows that were actually so low such that they could not sustain a steady drinking water supply anymore. And now I'm showing you a stream flow response in the same area with a basin that is highly dependent on glaciers. So what we can see is during the heat wave, we see a very strong response of the stream flow. But after the heat wave, we actually see normal flows again. So what this tells us is actually that glaciers are really important to balance our climate and to keep or to ensure a steady stream flow and drinking water supply, even after these kinds of significant or extreme events such as this heat wave. And this brings me to a summary. So in my talk today, we've seen basically that current empirical models that are used to simulate and project regional and global glacier melts, they have large uncertainties. And this is mainly due to the fact how these models are calibrated and to the fact that we actually do have very little local observations to constrain our models. And this might be that these models even underestimate the glacier melt at different spatial scales. And so what we've learned is that the attribution of regional glacier changes is not possible with empirical models, so we cannot attribute it to other variables other than temperature. Then empirical glacier models at regional and global scales are too sensitive to temperature changes, but climate change affects also other variables such as the surface reflectance. And we've seen that physics-based models can be used at local scales as well to model glaciers where we do not have any direct observations. And this is not possible with empirical models because of the large uncertainties. And then I showed you two examples of contributions of glaciers to hydroelectricity power and freshwater resources. So we saw that the decreasing glacier mass leads to scarcity and unpredictability of freshwater supply in the summer when the water demand is at its highest. And we can assume that with increased glacier loss, heat waves like this one will be even more devastating in the future. And this also largely depends on the timing of the heat wave, of course. And so my main takeaway message is that glaciers do play a key role in balancing our climate and our water systems. And melting glaciers, they don't just contribute to sea level rise, but they also contribute to a large extent to freshwater supply, and they impact our energy security and hydropower, agriculture and tourism for millions of people around the world. And we know that glaciers are losing mass at an increasing rate. And the United Nations have declared 2025 as the International Year of Glacier Preservation. So I really think it is very important to take ambitious action now. And I really urge the negotiators here to pursue these ambitious climate targets and to decarbonize now in order to preserve this beautiful nature for us and for the generations to come. Thank you. Are there any questions from the audience, please? Yeah.
So you talk about specific models to sort of evaluate the fitting of the glacier in communities that don't have observations.
Mm-hmm.
How are these communities using the results of these models? What do you anticipate them being able to use in regards to climate change adaptation?
Yeah, this is an interesting question. So I think the problem is that currently physics-based models are used at a local, at a glacier scale, but mostly for glaciers where we do have observations. And there has been a significant study 3 years ago, actually, where they published data from satellites from digital elevation models for each glacier. So we can see the thinning rate for each glacier that has now been used to calibrate these models. But this has been really recent. They're just the first studies coming out now, actually, that use this at a more regional or global scale. So basically, that is to say that it is still very much at the infancy to model these, or to model these glaciers. And the problem is, of course, as well that you don't. If you don't have any observations, you can't validate your model, right? So for this one community, I don't know exactly how they're using it or which model, whether they're relying especially on the empirical model or not. But I would assume that these physics-based models will be used more and more, especially now with the advances in satellite imagery.
Just a follow-up question to that. So with that being said, would you say that it's pretty important for these communities that will possibly have more direct observations of these
yeah, absolutely. Yeah, I think this is one of the main issues that the lack of observations has hindered this glacier model development. So we have, in my case, in my region, we do have 20,000 mountain glaciers, but we only have observation for 17 of these useful observations. That means we can really not constrain these models. And the problem with satellite imagery that we are using now is they have large uncertainties as well, such that we can only use the multi-year or even multi-decadal mean of the satellite images per glacier to constrain our models, which again leads to some uncertainties, right? So the consensus has always been that at a regional level or at a global level, they might, the biases cancel out, and they might kind of give you the, probably a good estimate, but at a local scale, we do have large uncertainties. But I think just with the advances that are already on the way, there might be more and more use for that.
I have a question. Mm-hmm. You said that as you go up the elevation, the albedo increases.
Yes. Yeah.
So how do you incorporate that into your physical model? Do you do actual measurements of albedo, or you use satellite?
Yeah, it's a good question. So what I did is, I trained a neural network model for my albedo simulations. So I used MODIS albedo data at each point in the glacier, basically, so that this is available at a resolution of 500 meters. And then I trained my model for each elevation separately, with input data from climate input data, but also topographic input data, such as elevation, slope, angle, and these kind of things. And I found actually that my model is replicating MODIS data really well, but the problem is that MODIS data usually underestimates the albedo. So I still needed to insert a small albedo correction factor into my model. But so I'm using elevation-based albedo that is different for each elevation, and that is based on physical properties. Yeah, if there are no more questions, then I thank you. I wish you a nice rest of your afternoon. Thank you.